All right. Well, Shannon, you got another question. Why don't you go ahead?
I do, and I might be getting a little ahead of myself here, but Manish on YouTube asks, "How will we benefit from NISAR's mission research?"
Why don't we come back to that one in just a minute? We'll let
Perfect.
Yeah,
Paul
I think
build up to
we're
that.
going to have a lot to say about that as we go forward. Yeah.
So how about this? Let's answer that question right now.
Exactly.
All right, let's get started then talking about these two examples, these kind of specific examples from the many, and I mean many, different Earth science missions and programs that NASA supports. These are two upcoming missions, NISAR and Delta X, meaning they're still in development, getting ready to deploy, and they're very different types of missions. And so together they give a sense of the wide range of methods and perspectives that NASA uses to help understand how our planet works and how it changes. So let's answer that question. Let's talk about NISAR, Paul. Starting with, what is it?
Well, NISAR is a fantastic mission that I have the honor and privilege to be the project scientist for. NISAR is an acronym. So it's a set of words that are put together into an acronym. N stands for NASA. So that's another acronym. The I stands for ISRO, which is another acronym, stands for the Indian Space Research Organization. And the S stands for synthetic. The A stands for aperture, and the R stands for radar. So NASA ISRO Synthetic Aperture Radar mission. Very complicated. We tried to come up with a better name, but it was very difficult, and we just stuck with that. So it describes that we are in a partnership with the Indian Space Research Organization. NASA and ISRO are equal partners building this satellite together. And I like to think of the satellite as effectively a radar that makes 3D time-lapse movies of the Earth. And we'll talk about the aspects of that in a bit. But first, I thought I'd kick it off by showing an animation, which is kind of like a 3D animation of the spacecraft itself. That would be graphic number 1. That could be brought up. So this is showing in 2 years from now, when we launch in 2022, the spacecraft is stuffed into an Indian space vehicle, and then it has to be deployed. So here you can see the deployment of a very complex boom with 4 joints. You can see the boom is now being extended to its 9-meter length, and then it rotates up and gets into its final position to deploy a 12-meter diameter, that's 36 feet roughly, reflector, gold mesh reflector. So this is a huge system that we are launching into space. 12-meter reflector, 9-meter boom, and a 5-meter spacecraft packed with electronics. 2 radars, one from NASA, one from ISRO, and a lot of telecommunications equipment to get a huge volume of data from space to the ground. So that's what the system is, and these 3D IMAX movies are to measure deformation. And the technique that we use for that is by taking an image, comparing it to the image at another time step, and another time step, and another time step, and looking at these images as a meter stick to measure the motion of the Earth to millimeter precision, and the changes in the reflectivity of the Earth to very, very high precision as well over time. So we can see changes of all the land and all the ice-covered surfaces over the life of the mission.
Wow. So to millimeter precision from space.
Yes,
That's
pretty from
impressive.
1 million meters of space, you can measure it to 1,000th of a meter precision. It's really phenomenal.
Very cool. Well, tell us more about how you do it. I mean, you use radar, right?
Yes. Okay. Well, let's see. First of all, let's look at graphic number 3, which shows you an animation now of how the system operates. So we're flying along at 7,500 kilometers per second, and we're sending pulses to the ground roughly 1,000 times per second. So each one of these little potato chips you see flying to the ground is traveling at the speed of light, measuring that then reflects off the surface, and some of that energy goes back to the radar and is received. Now, as you collect that data, you can see that as you collect more and more pulses, you can build up resolution of the image. That's in the top right portion of your image. You get a radar image like that that is high resolution after you collect enough of these pulses to do so. So that's the synthetic aperture part. It's like having a very large lens in space that's 10 kilometers long. It's not that long, but it's synthetically that long by processing the data in a particular way to get this high resolution imagery. Then once we have that image, we fly over the same spot again, make another image that looks just like it, and you can think of the radar wave that we transmit kind of like a meter stick. And we're measuring the changes in the length of that meter stick as the Earth moves below the satellite.
Very cool.